This is going to be a short addendum to 10.3 and 10.4. We talked about arc length computation formula for polar curves, but I don't remember talking about area of surface of revolution for polar curves, or surface given by rotating polar curves around x-axis or y-axis. This formula can be used for the surface area of a surface of revolution given by a polar curve when it is rotated by x-axis, because the radius is y, so we have 2 pi y of theta, and ds is this. We already talked about it in arc length computation. This formula down here, on the other hand, can be used when the polar coordinate is rotated with respect to the y-axis. Consequently, the radius of rotation is x. Again, ds computation is pretty much the same as before. Let's do a computation here. Let's begin with cardioid again. R equals 1 plus cosine of theta. And let's rotate it with respect to the x-axis. And here's the picture actually. Excuse me. And here it is. We do not need entire cardioid from 0 to 2 pi, because what we're going to do is rotate the upper half of cardioid, first and second quadrant, which is represented in solid curve. Rotated with respect to the x-axis, then the bottom half will be covered automatically. So I don't have to worry about 0 to 2 pi. Actually, that's going to be inaccurate. Integral will have to be done from 0 to pi. And here is the 3D picture of the cardioid. It's a little bit difficult to see, even though I put some transparency in there. It almost looks like a ball, unless you're looking at from this left-hand side, where we have some kind of pinching going on, but it's still hard to see. This may be a bit of cheating, but we can see things better if you just rotate it only from 0 to pi, and then look at only upper half of the cardioid like this. So top kind of looks like a dome, but if you look at from behind, look from below, then you have a cardioid shape forming here, and kind of like this. Of course, you can go back to 2 pi. Now let's do the computation, and that's gonna be long and complicated. Let's begin with the formula 2 pi y, because rotation is with respect to the x-axis, so the radius of rotation is y, and then r squared plus r prime squared times d theta is nothing more than the ds computation, which we use for arc length. And the arc length computation, we already did this computation. It wasn't simple, but we did it. R squared is like this complete square, R prime squared is like this, and we did all these computations to get this third line over there, and then using half angle formula backwards to get the fourth line over there. That's basically it. This one. And by taking half angle formula here, we get 2 times cosine of theta over 2. Now, I do not have to worry about absolute values here, because cosine of theta over 2 is positive when theta is between 0 and pi. Cosine of theta over 2 goes only from 0 to pi over 2, because theta goes only up to pi. So everything is positive. I don't have to worry about absolute value. So let's just distribute it around, and cosine of theta 2 is multiplied here and there. Now what we do, we apply the conversion formula. Sine times cosine is 1/2 of sine of a minus b plus sine of a plus b. So we end up with something like that. And sine times cosine, kind of similar. We have the same formula because sine times cosine, only the angles are different. 2 theta versus theta over 2. So sine of half of sine of a minus b plus sine of a plus b. That's the formula. So 3 theta over 2, 5 theta over 2. After a little bit of simplification, and then applying the fundamental theorem of calculus here, we end up with 32 pi over 5, which is precise value. Long and complicated, yes, and then we use multiple techniques in chapter 7, but this is one of very rare example that you can complete the surface area computation for polar curves. Rotation about y-axis is almost the same actually. Here in this computation, instead of 2 pi y, we need 2 pi x. So the sine of theta will have to be replaced with cosine of theta. So we have cosine of theta over here and cosine squared of theta over there, and we'll have to use a little bit different technique regarding this power reduction formula, but in the end, using the convergent formula from product to sum will come into play in the end, and you're going to get a certain value. And if you want to challenge yourself for that kind of thing, please go ahead. Otherwise, I'm going to bury this as an optional topic. Excuse me. Let's move on to the final problem of the area computation. In some cases, polar curves can have multiple loops. Some of the easiest cases are covered here. This one, this is a Limassong. This r plus 2 cosine of theta. This 2 value is a parameter, and if this value is 1, then we have a cardioid. Less than 1, then we have Limassong that is that actually goes a little bit to the left hand side, no inner loop. When this value over here is like 2, greater than 1, then we are going to get inner loop. And we have to find out area enclosed by the small loop. So how do you find out? Well, of course, we are going to use this formula here. That's straightforward. And then that r value is, well, given as 1 plus 2 cosine of theta here. So no problem there. Problem is almost all the time integral where to where. So you have to find out in which angle this inner loop begins and where it ends. So it goes like this. When this radius r comes back to 0, and that's when cosine of theta is negative 1/2. So we have theta equals to plus or minus 3 pi over 2 pi over 3. Actually, this doesn't look too good. I prefer to have 2 pi over 3 and 4 pi over 3. So we can calculate the area of the inside. Oh yes, I do have it here. Excuse me, I should have run everything all over again. Okay. So outside, the blue picture is running from negative pi over 2 pi over 3 to 2 pi over 3. So we have that. But the question this problem asks you is the inner curve. That's when 2 pi over 3 to 4 pi over 3, because that's when polar angle is pointing toward the opposite direction. I mean, pointing toward second and third quadrant, and the r value is negative, so we have opposite movement. Consequently, we have this inner loop, and that's generated by like that. The red curve is the inner loop, 2 pi over 3 to 4 pi over 3, and those are inner and outer together. Consequently, the area must be, find the area between a large loop and this enclosed small loop. Okay, I see. I have to find an area of this inside this blue region minus this red region in this picture. Blue minus red. So this is going to give me blue region, and that's going to give me the red region. Calculate the integral, and then you're going to get, well, the detail is left to the students. You can use complete square, and then for cosine of theta is easy, but for cosine squared, you're going to have to use that power reduction formula to calculate it. In the end, you're going to get 3 square root of 3 plus pi. I wonder what you get if you simply calculate this integral from 0 to 2 pi. Well, you get something different. So there's a trap. This one is a little bit harder problem. Find the area between large loop and the enclosed small loop of the curve. A little bit more complicated curve, so it's a little bit more complicated. Curves kind of, well, it looks like this. So the area between large loop and a smaller loop, so you can divide the region, well, kind of like this. Blue part from 0 to pi over 2, and the red region pi over 2 to pi over 3, and then green region 3 pi over 2 to 2 pi. But you don't really have to worry too much about this second quadrant part, because all you have to do is calculate this right hand side and then simply double it. So just calculate the integral. Well, okay, in this program I just calculated everything, but that wasn't really necessary. Just calculate 0 to 2 pi for the blue, inside blue, and then 2 pi to pi to get inside red. Subtract one from the other. Then we have the right hand side here, the region between blue and red. And if you simply double it, then you're gonna get the area you're looking for. Well, problems can be as bad as it can get in polar coordinates, so you have to be a little bit careful about those kind of things. And almost all the time, the difficulty is coming from the angle where the integral begins and ends, not in the integrand part. Okay.